MathCounts people, here we go. We've got warm-up 8 from the 2024-2025 handbook. Okay, so I've already solved all these, but instead of showing you my chicken scratch answers, I'll try to explain it a little bit closer. Hope you guys are having a good Thanksgiving break. Here we go. All right, a regular 12-hour analog clock reads 12:24. How many degrees are there in the measure of the smallest angle formed by the hour? So they're talking about this angle right here between these two hands. We want to know how many degrees that is. Okay, well, I know that this big hand is pointing at 24, but I can't really tell where the small hand is pointing. And I think they have it pointing at the wrong number just so that people guess wrong. So basically, if we were looking at the clock, how do I say this? Okay, so this clock has 360 degrees in it, yeah? Yeah. So going into full circle is 360 degrees. So we've got 360 degrees total. Now this particular clock only has 60 increments in it. So that means we've got 60 increments. So each minute mark is representing 6 degrees. Does that make sense? I hope so. Okay, so I want to know how many minute increments are from here to here. And again, I'm struggling with this top part, how to define how far that is. Now, as the minute hand is going around, the hour hand is slowly going this way. So like when it hits 30 minutes down here, this is going to be halfway between 12 and 1. Well, this is less than halfway, because right now we're at 24 minutes. 24 out of how many minutes? 24 out of 60 minutes. Okay, what is 24 over 60 reduced to? Well, 12 goes into both of those numbers. 12 goes into 24 2 times, and it goes into 65 times. So I am 2/5 of the way from there. And wouldn't you know it, there are 1, 2, 3, 4, 5 minutes between 12 and 1. So that tells me that this minute hand is pointing at the 2 right here. So I've got from 2 to 24 that I'm going to go to. And remember, each minute section here is 6 degrees. So I'm going to go 22 degrees. No, not 22 degrees. 22 minutes. Each little minute mark between 2 and 24 is 6 degrees. Multiply by 6, and we do get 132. There's our answer. Next one. A fair coin is flipped 5 times. What is the probability that there are at least 2 tails and at least 1 head? Okay, so I know that the total possibilities would be 2 to the 5th power. Because I can either get a head or a tail, and then it goes, each one's going to split off, make 2 more possibilities. So we know that the total possibilities is going to be 32 possibilities. Because you can either do heads or tails 5 different times. So basically 2 times 2 times 2 times 2 times 2. All right, so what I don't know is the top portion of it. How many of these 32 outcomes have 2 tails and at least 1 head? Well, we have to think of the different cases where this could happen. So if I have 2 tails, that would mean I have 3 heads. So that's one outcome that would satisfy our probability here. We have at least 2 tails, and we have at least 1 head. Okay, we could also do 3 tails, and that would make 2 heads. And then we could have 4 tails and 1 head. Okay, those are the only cases that would satisfy what we have here, where we have two tails and at least one head. So here I have two tails, I have at least one head. I've got three tails, I have at least one head. I've got four tails, I have at least one head. That's it. Those are the three situations. So now we want to find out how many ways that we can flip a coin and get two tails and three heads. Well, there are 5 different coin flips, but in this case, 2 of the outcomes would be the same, and 3 of the other outcomes would be the same. So this would be 5 factorial, but then 2 of these outcomes are both tails, so those are the same, so I need to divide out those that are the same. And then 3 are also the same. So this would end up giving us, 5 times 4, that cancels these, divided by 2. That gives me 10. So there's 10 outcomes when I have 2 tails and 3 heads. Now the next one's going to give us the exact same probability, because this is 5 factorial divided by 3 factorial, 2 factorial. Same exact outcome, we're going to get 10 for that one. Last one, 4 tails and 1 head, 5 factorial, 4 things are the same, and then we've got the one thing over here is not the same. So we would start reducing, and we would just be left with 5. So from this case, I've got 10 outcomes. From this case, I've got 10 outcomes. From this case, I've got 5 outcomes. I have a total of 25 outcomes. So we have 25 over the total 32 outcomes. I guess you could have, we don't worry about that. All right, next. Chris is throwing darts at a circular dartboard. Okay, circular dartboard. So a lot of times it's nice just to make a drawing of what's going on. So there's my circular dartboard. First dart he throws hits the dartboard close to the edge. It's only 3 inches away. So 3 inches away, there's the first dart. Goes in right there. Let's say this is the center of the dartboard. The second dart, a better throw, lands only 2 inches away from the center of the dartboard. Okay, 2 inches away can be anywhere in a little circle here. So 2 inches away could be anywhere around that circle right there. Say that's 2 inches away. The 2 darts are 10 inches away from each other. What's the smallest possible radius of the dartboard? Well, if we're going for the smallest possible radius, we would not put the other dart right here, because then we would have 2 here, 10 here, 3 here. That would be a radius of 15. That's actually the biggest radius you could get. What we want to do is put the 2 over here. Because now when we have a distance of 10 from here to here, what we actually have is from here to here being 8. 8 plus 3, 11, is the smallest distance possible. Because since we're on this side of it, this 10 doesn't become part of our radius. Only 8 of it becomes part of our radius right here. So 8 plus 3, that would be the smallest radius possible, 11. Next, x plus y equals 3 and x minus 1 equals 1. What's the value of x squared y squared plus 6xy? Okay, so we have a systems of equations here. We can just add the 2 equations together. If we add the 2 equations, we would get 2x, and then the y's would cancel. And then 4, x would be 2. So if x is 2, I now know that 2 plus 1 is 3, y is 1. Now we just plug it in. 2 squared plus y, which is 1 squared, plus 6x is 2, y is 1. So we've got 4 plus 1 plus 12. 17 is our answer. Next. How many integers from 2 to 147 have square roots that are whole numbers? Okay, well, I know that my first square root that would work would be root 4, which is 2. And then my last root would be root 12, which is square root of 144, which is 12. My calculator's out of there. So basically, it's not 12 minus 2 because we're including this 2. So it's not 10, it's actually 11. And another way to think of it is we're going from 1 to 12, but we're using everything but 1. So going from 1 to 12 without using 1, that means we're using 11 of those numbers. So 11 integers would work. Next, Al and Bert regularly buy comics at their local comic shop. Every time Al shops, he buys 10 comics. Okay, so let me write that. Al gets 10 comics. Bert, on the other hand, he's getting 8 comics. At the end of the year, they compare comics they bought and are surprised to learn that they each bought the same number of comics. Okay, so they're going to have the same number. If they each visited the comic shop at least once each calendar month, what's the fewest number of comics Al and Bert could have bought all together? We're supposed to add up Al and Bert. Okay, they have to go once a month at least. So, if they go once a month at least, if this guy goes once a month, then this would be 120 comics. Now, if we did once a month for this guy, that would be 96 comics. But this guy couldn't go 96 because he wouldn't be able to go once every month. So we want to take our bigger number and just check and see, hey, is it possible for him to go just once a month? Because we want the fewest number. So I want the fewest number of visits to the comic shop. So I can't do this guy going once a month because then we couldn't get this guy doing it. We couldn't get enough comics for this guy. So what I would do at this point is just ask myself, does 8 go into 120? And it does. This guy would end up visiting 15 times to get 120 comics. So Al goes once a month, so he gets 120 comics. And then this guy would go 15 times during the year, at least once a month and then 3 extra times. And they have 120. Now, this is the tricky part. It's all together. You might be tricked into thinking, oh, my answer is 120. No, it's all together. They would have to get 240. So the fewest number of comics they could get would be 240. Next one. Oh, burps. All right. A factorial plus B factorial plus C factorial plus D factorial is 29. What is the value of A times B times C times D? All right, so let's look at our factorials. 1 factorial is, of course, 1. 2 factorial is, of course, 2. 3 factorial is, of course, 6, because this is 3 times 2 times 1. 4 factorial would be 4 times 3 times 2, which should be 24. And 5 factorial ends up giving us 120. All right, I know none of these numbers can be 5 factorial because 120 is way too much. I know I have to use 4 factorial somewhere. Because if all of these were 3 factorial, that would only add up to 24, not 29. Okay, so it says all of these are positive integers. Now, it doesn't say that they're all unique positive integers, so they're just all positive integers. So they could all be 4, they could all be 3, they could all be 2. But anyways, I know that I have to use 4 factorial, because if these were all 3 factorial, it would only equal 24. So I'm going to say, okay, let's say if I've got A, B, C, and D factorial, let's just say that the D factorial is 4 factorial. All right, so this is 24. How much is left for the other 3? Well, we only have 5 left. If I've got 3 items and they have to add up to 5, I now know what they have to combine to. I need 2 of these and 1 of these. Because if I have 2 factorial and 2 factorial, that's 2 plus 2. And then this is 1 factorial, so that would be 1. There's the 5 that I needed left over after I used the 24. So that means A is 1, B is 2, C is 2, and D is 4. Really doesn't matter the order. And this is A, B, C, D. So we're just multiplying all these so that we get 16. All right, we are moving now. All right, if x is a positive real number, so it has to be a positive, such that x squared plus 2x equals 80, what is the value of x to the third plus 3x squared plus 3x? Okay, so for this one, I would go ahead and solve this. This is a quadratic, so the quadratic should give us 2 solutions. First thing I'm going to do is get 0 on one side, so this would give me x squared plus 2x minus 80. Okay, then I would try to factor it. Is there anything that multiplies to give me negative 80 but adds to give me 2? So I look at this number and this number. And yes, there is. I could use positive 10 and negative 8. So this would factor into x plus 10 and x minus 8. Set these both equal to 0 because the principal zero product says that if we multiply and they equal 0, one of these is 0. So x plus 10 might be 0, x minus 8 might be 0. I get 2 answers. X equals negative 10 and x equals positive 8. Only one of these satisfies our conditions. We have a positive real number solution. This is a negative number, so that one doesn't work. X must be 8. So now I just plug 8 into that original equation. I do 8 to the third plus 3 times 8 to the second plus 3 times 8. So 8 times 8 is 64. 64 times another 8 is 512. This is 8 times 8, that's 64. So I'm doing 3 times 64. And 3 times 64 is 198 and 92. Yeah, 192. And then 3 times 8 is 24. Add them all together. What do you know? You get 728. 2 more. And then I get to go home. The sum of 2 positive integers and their product is 1. Oh, is 1 less than the product of 5 and 7. Okay, so the sum of 2 positive integers, we'll just call them x and y. So it's the sum of the 2 numbers and their product. So plus xy is equals 1 less than, minus 1 at the end. The product of 5 and 7, so 5 times 7. All right, lovely. So over here, I can tell that x plus y plus xy equals 35 minus 1, 34. Now, there are, since we have two variables in here, there's an infinite number of combinations of x and y's that can give us 34. But our x's and y's have to be integers. So the first time that I solved this, I decided, you know what? Since they're integers, I'm just going to rely on my math sense and my calculating to see if I can find the numbers. You know, I noticed that I couldn't use 1. I mean, I could use 1, but I just kind of started playing around with some numbers. Like you might start with 5s. Maybe both of these are 5s. That's what the book kind of says, is they started with 5s. I didn't quite do that. But like if you do have 5 and 5, that's 10. 5 times 5 is 25, so you get 35. So if x and y were both 5, you would get 35, which is a little too much over. So then you might start playing around with your two different combinations. This is where your math sense kicks in. And you just start playing around with numbers that you could plug in there. And what happens is eventually you'll come across 4 and 6. And then what you get is 24 plus 10, that is 34. That is actually the only combination that works. And then you need to find the product of the two positive integers. This is the product right here. So 24 is your answer on this one. I think that's probably the best way to solve this one, is to kind of guess and check and just do quick calculations in your head to do that. There is an algebraic way that we could do this. What kind of algebraic? Yeah, kind of. So here's what you could have done instead. So, or, I did not think of this one. This is one of the suggestions in the book, but it works. They said, what if you added 1 to both sides? Okay, let's do that. If you add 1 to both sides, I'm going to leave this as 5 times 7 because it's going to make sense at the end. So here, I've got 4 terms. And if you're good at factoring, you probably know one of your factoring methods is to do the factoring by grouping. So if I want to factor this one by grouping, I would probably rearrange it. You might see it already if you know how to factor by grouping. I would rearrange this as x and then xy plus y plus 1. So when you're factoring by grouping, you would group these two terms and you would group these two terms over here. So I would look for a GCF inside of these. So the greatest common factor for this was x, and I would be left with 1 plus y. Over here, I would factor out a 1, and I'm left with 1 plus y, or y plus 1. It's the same thing. So since these two are the same, that's one of my factors. Since these two are the same, that's my other factor. So this times this equals this times this. So you can just say, oh, y plus 1 must be 5, and x plus 1 must be 7. Subtract 1, y is 4, and my other number is, subtract 1, x is 6. 4 and 6. So you could do that one algebraically. In the time that you took to think of that method, you probably could have just guessed and checked and got your answer a lot faster. Last one. Oh, this one. This one is delicious. There's so much there, so many numbers. All right, so if you were actually taking the section, what is it that's called? What round is that called? where you do the 30 questions in 40 minutes. I can't think. It's been a long day. Anyways, this is the type of problem that I would leave to the very end because there's so much stuff to digest on this one. So this is definitely the stuff, because the smartest way to take the test in the competition is get through as many questions as you can, as fast as you can, with whatever time is left over, then try to go over the ones that look like might take a lot more time. And with all these different numbers in here, this one's definitely probably something that's going to take a little bit more time. So let's look at this problem. So a theater sells tickets at adult and child prices. So we've got adult tickets and children's tickets. One day the theater makes $1,380 in sales. So they make $1,380 in sales. So if we make this the number of adults, and this is the number of children, so the price, let's just call little a the price of the adults and little c the price of the children. So little a times the adults plus little c, the cost of the children, times the number of children, that's what we would get here, equal to $1,380. So there's multiple things that we don't know. We don't know how many adults there were. We don't know how many children there are. And we don't know the cost of the adults, and we don't know the cost of the children. So we're missing a lot in that first sentence. Next thing it says is, if all the tickets were adult tickets, the sales would have been $1,500. So if we had all adults, we're looking at $1,500. Now that does kind of tell us something. It tells us, if I subtract 1,500 from 1,380, it tells us that the adult tickets are more than the children's tickets, and the difference in costs between the adults and the children would be $120. So the children's tickets have to be divisible by 120 at some point. All right, moving on. If instead all the tickets were upgraded to 3D for $2 per ticket, then the price would have been $1,580. All right, so if I increase my cost by $2 per ticket, so this is the total number of tickets. This is adults plus children. If I do that, then it's going to be 1,580. All right, this finally tells me something I can use. This tells me that if I add 2 to this, the difference ends up being a difference of $200. So the difference between what it did cost and if I add 2 to everything, that's a $200 cost. Now, how did I get $200? The difference of 200? This is 2 times the adults and the children is $200. So this is telling me that I sold 100 tickets. Whew, finally found something out. I know I have 100 tickets. Awesome. What else? Well, I know, dang it, stupid lights. Seriously? All right. I wasn't moving around enough. Where was I at? All right, so I know that if we have a $2 increase, that leads to a $200 increase, and this is per ticket. This is leading to a $200 increase in the price. So that's how I know that I have 100 tickets. Whew. All right, so we are looking for the number of children's tickets. So here's the first thing I can write. I know that the adult tickets plus the children's tickets equals 100 tickets total. All right, awesome. Know that. Next thing that I know that the children's tickets cost $9. So $9 for the children's tickets equals $13.80. Okay, so the next thing that I know is that if I have the number of adults, so little a, this is going back to this part, right? This part over here. I know that if I've got the adult price times the adult tickets, that this is going to end up being $1,500. And that's if all of them are adults. And remember we said that there's 100 tickets? So if I have 100 adults, this is saying that the price times 100 adults would be $1,500. I now know that the price of the adults is $15 per ticket. Whew, this is really all over the place, isn't it? Okay. I don't know why I did this 120. I didn't need that. Okay. Are you with me now? So $15 times the adults. How did I find $15? Because all of the adult tickets, all of the adults times the adult ticket price, that would have been $1,500. I know that there were 100 tickets sold. So now I know that the adult price is $15 per ticket. They told me the children's price was $9 per ticket. I now have a systems of equations. Now on this one, I want to find out how many children tickets did the theater sell. So the easiest way to do this is to set up a system of equations where we get rid of the adults. So let's get rid of the adults. Let's multiply both sides of this equation by -15. That leaves me with -15a minus 15c equals -1,500. Yeah. A's cancel. -6c equals, oh, that's the number, -120 divided by -6. C is equal to 20. I know there's an easier way to do this, but when I first solved it, that's the craziness that I went through. There you go. We know that there's 20 children's tickets. That was a lot. All right, guys, math hard. Have a good Thanksgiving. I'll see you guys later. Bye-bye.